In the last lecture, you were introduced to what is called Hooke's law. Hooke's law is a description of the force that's exerted upon a mass due to a spring. When that force is incorporated into the motion of an object, it leads to a very important type of motion, which is called an oscillation. What we seek to do here in this lecture is describe an oscillation in terms of conservation of energy and in terms of energy transfer. Now, when I demonstrated an oscillation to you, I did so vertically because it's easy to do it that way here in my classroom. Well, let's go ahead and remove the complication of the force of gravity and describe what happens horizontally. When it comes to describing a horizontal oscillator, we do so in the following way. Okay, so first of all, usually what we draw is an attachment, like so, or a wall that the spring is attached to. And then right here is a mass M that's attached to a spring, and the spring has a spring constant K. Recall that the spring constant K is a measurement of the stiffness or looseness of a spring. Let's say that right here, for example, is the equilibrium position. The equilibrium position is the unstretched or uncompressed position of the spring. This is all going to take place, by the way, on a horizontal frictionless surface. So for that reason, quite frankly, we don't even really bother drawing the surface itself. Okay, now let's say that I stretch out the spring and I do so at displacement from the equilibrium position, which, if you recall, is always referred to as x, like so. Okay, so right here is the displacement vector x in this direction, and then the spring force acts back in the opposite direction, always towards the equilibrium position. The spring force is an example of what is called a restoring force. A restoring force always tries to bring the object back to the equilibrium position, in this case, the equilibrium position of the spring. Okay, so right here is F spring, like so, and its magnitude is equal to K times X. Okay, now identical to this situation involving stretching out a spring is the following situation involving compressing a spring. For an idealized spring, there's no physical difference between stretching and compressing. So let's say that I compress a spring like so. So here's the equilibrium position. And then once again, right here is the displacement vector x in this direction as I compress the spring. The spring force, however, is still back in the opposite direction towards the equilibrium position. Once again, the spring force is an example of a restoring force. So right here is F spring, back towards equilibrium. At this position, its magnitude is equal to K times X. Okay, now in order to ultimately describe energy conservation for an oscillation, we first of all have to briefly calculate the work done by the spring force when either stretching or compressing the spring. I'm going to use my stretching diagram here to illustrate. So let me go ahead and erase this. And now here's a brief description of calculating the work done by the spring force. Okay, so the work done by the spring force is going to be the following. Okay, recall how we calculate work. It's force times distance. In this case, however, the force vector is in the opposite direction of the displacement vector. So then therefore, we're going to have a negative sign for that reason when calculating work. In this case, however, the spring force is not a constant. As the value of x continuously changes as an object oscillates, the spring force continuously changes in value. Strictly speaking, the only way to calculate the work done by such a non-constant force is by using the methods of calculus. That's, of course, way beyond the scope of this course. So here's then how we go about doing so algebraically. What we do is we multiply, once again, force times distance, but in this case, we use the average amount of force. We use the average amount of spring force from starting off here at equilibrium, which is 0, to ending up here at the displacement x, so the spring force is equal to K times X. The average of those two values is 0 plus kx over 2, or just kx over 2. So then we take the average spring force, kx over 2, multiply it by the displacement, x, but then once again recall that there's a negative sign that is present here because these two vectors are in opposite directions. So then therefore the work done by the spring force is negative 1/2 kx squared for that reason. Okay, this right here is analogous to the following. Recall from gravity. For example, if I take an object and I lift it vertically like so through a vertical displacement, as we've seen, the work done by gravity is negative mgh. Therefore, the work done against gravity is positive mgh. And that then becomes the potential energy of the object, which is transformed into kinetic energy as the object falls. Same idea here. Let's say, for example, to take a spring and I displace it from equilibrium. Okay, I obviously did work in doing so and I used energy, but initially it looks like the energy that I used disappeared. And then, for example, if I take the spring and release it like so, it gains kinetic energy as it moves back towards the equilibrium position. It looks like that kinetic energy came from nowhere. The only way in which we can reconcile these two questions is to recognize that another form of energy must be present, and that's what's called spring potential energy. So then therefore, if I take the spring and I displace it like so from equilibrium, as we just have calculated, the work done by the spring force is -1/2 kx squared. Therefore, the minimum energy that I have to use to overcome the spring force, what is called the work done against the spring force, that then becomes +1/2 kx squared, and that is then therefore the spring potential energy. And then this spring potential energy of 1/2 kx squared is transformed into kinetic energy as the object, for example, moves back towards the equilibrium position. So this is the same series of steps now for the spring force as we did earlier for gravity. Really the only difference here mathematically is that instead of giving mgh for the gravitational potential energy, here in this case we have 1/2 kx squared for the spring potential energy. So here's then how we write this out. Okay, so then therefore, the work done against the spring force is equal to the opposite of the work done by the spring force, which is equal to the negative of -1/2 kx squared. This is equal to +1/2 kx squared, like so. And so then therefore, the minimum energy that I use to overcome the spring force, the work against the spring force, +1/2 kx squared, that then becomes the spring potential energy. Okay, so I'm going to go ahead right here and write the spring potential energy as U sub s, and that's equal to 1/2 kx squared. And now using conservation of energy, we can go ahead and easily describe an oscillation. So describing an oscillation using conservation of energy, as you'll see, is actually quite simple and straightforward. The reason why we teach you the spring force here, by the way, in the context of conservation of energy, is because mathematically it's really easy to deal with. Okay, let's immediately take a look at an example. I'm going to go ahead and do some erasing here to illustrate that example. Okay, copy the example down into your notes as I read it to you. Okay, a fixed horizontal idealized spring is attached to a mass of 1 kilogram on a horizontal frictionless surface. The spring constant equals 10 newtons per meter. The mass initially stretches the spring a distance of 0.5 meters from the equilibrium position, and it's released from rest. We're going to calculate two things. In part A of the problem, we're going to calculate the speed of the object as it passes through the equilibrium position. And then in part B of the problem, we'll calculate how far on the other side of the equilibrium position the mass compresses the spring. Okay, so part A looks like this. Okay, so right here is initially the stretched out spring like so. So here's the equilibrium position. This distance here is the displacement x that's given to us as 0.5 meters. We then release the object from rest. The initial velocity is equal to 0. And then we're given that the mass of the object is 1 kilogram and the spring constant K is 10 newtons per meter. Okay, and then we're asked to calculate the following. I'll draw a second diagram here to illustrate. We're asked to calculate right here the speed of the object like so, the speed v, as it passes through the equilibrium position. Because the energy is conserved, we'll simply write the following expression. The spring potential energy that we start with turns into, let me write it like this, the kinetic energy that we end with as we pass through the equilibrium position. And now we'll just fill in the two terms here, and then we'll calculate the speed v. So we start off with spring potential energy of 1/2 kx squared. That is then transformed into kinetic energy as the object passes through the equilibrium position. Kinetic energy, if you recall, is 1/2 mv squared. And now we just solve for the speed v. Okay, when we solve for the speed v, the 1/2s here cancel out like so. The mass, however, nor the spring constant, neither of those two values cancel. The speed of the object in part depends upon these values. So now let's go ahead and solve for v. In order to do so, I'm going to divide the m here to the other side. Let me do it right here, like so. And now what we do is we take the square root of both sides, taking the positive value what we do to obtain the speed. So the speed is equal to the following expression after you do the math, like so. And now we'll go ahead and plug in our values here, and when we do, we end up with an answer that's in terms of meters per second. All right, so I have the square root of, first of all, 10 divided by 1 underneath the radical sign there, and then multiplied by 1/2 meter. And this comes out to be a speed of 1.58 meters per second. Okay, then in part B of the problem, basically the situation now just happens backwards. All of the kinetic energy that we now start with at the equilibrium position turns into the exact same amount of spring potential energy when we compress the spring. And then the unknown is to calculate how far we compress the spring. As you could probably guess, of course, it's going to be equal to 1/2 meter. Here's, however, how we show that for part B. Okay, let me do a little bit of erasing here to do so. And now let's draw the diagram for B in the following way. Okay, so now what we do right here at the equilibrium position is we're passing through with an initial speed V0 of 1.58 meters per second. That's of course what we calculated in part A. Okay, and then right here is when we compress the spring like so. So here's the equilibrium position. We end up at rest here for an instant, and then the unknown right here in the diagram is the displacement x. Okay, the energy transformation just happens backwards in this case. That is, all the kinetic energy K that we start with here at equilibrium turns into the exact same amount of spring potential energy when we compress the spring. So the kinetic energy that we begin with depends upon the speed V0, so that's 1/2 m V0 squared. And this then equals the spring potential energy on the other side as we compress the spring, 1/2 kx squared. So all the kinetic energy that we start with at equilibrium transforms into the same amount of potential energy on the other side. Okay, obviously this expression here is the same expression as it was mathematically for part A of the problem. So if we went through the motions here and solved for x, we of course would end up with the same value as before, and that would be 0.5 meters. This object will oscillate in this manner forever, provided that the spring is idealized and it's all taking place on a horizontal frictionless surface. The spring will alternatively be compressed and stretched out 0.5 meters from equilibrium every single time, and the object will pass through the equilibrium position with a speed of 1.58 meters per second every single time. The object will execute an extremely important type of motion. It's called simple harmonic motion, and the object itself is called a simple harmonic oscillator. As we'll see later on in the course, this is the starting point for describing anything, for example, associated with waves, which we'll get to, however, at a much later date. But for now, the object will execute simple harmonic motion. Simple harmonic motion, by the way, is abbreviated as SHM. There we go. And the object itself is called a simple harmonic oscillator. A simple harmonic oscillator is abbreviated as an SHO. Okay, make sure that you have this important information written down in your notes now as I go ahead and complete this lecture here.